Chapter 8 will be broken into two lectures. The first part here will be looking at thunderstorms, the distribution of thunderstorms, the distribution of lightning coming from those thunderstorms around the globe and the US in particular, also atmospheric chemistry involved with lightning, the distribution of wildfires, and we'll also look at the distribution of tornadoes across the United States and projections in the future as well. In Chapter 7, we really covered what I would want to talk about with floods and droughts, so we will not cover that again in Chapter 8. For the introduction, storms, floods, and droughts represent major deviations from typical normal conditions. The duration and intensity of these atmospheric events vary considerably. They are important for the regional climate. Severe storms are a result of imbalances in the distribution of energy. So these storms redistribute energy and are important for climate concerns, moving energy about the system. Why do we care about thunderstorms in particular? Well, they're a great water resource. If you look at the global distribution of thunderstorms, you'll find that's where the best agriculture is, because especially for the mid-latitudes, thunderstorms happen during the warm season, during the growing season, so it gives you your source of water when you need it. They also redistribute moisture and heat in the atmosphere, and they cause plenty of property damage and sometimes injuries or death. What elements are really required for any old thunderstorm to form? Well, you need moisture, you need an unstable atmosphere, what's called conditional unstable atmosphere. That simply means that the atmosphere is unstable enough so if you create a cloud, that little bit of latent heating during the ascent of that cloud forces that air to be warmer than usual because the latent heat adds heat to the air, and that forces the instability. So the condition required for instability is that cloud formation, and that's typically the state of the atmosphere needed for thunderstorm creation. You also need an initial trigger to trigger up the uplift in the first place. So that could be a large-scale cold front, it could be a mountain, it could be extreme surface heating in the afternoon. So just triggers to start this process off. Now, severe thunderstorms, which by NOAA are declared as thunderstorms that have 50 knots or greater wind at the surface, either straight line winds or tornadic winds, large hail, 3/4 of an inch or larger, or if they have a tornado hitting the ground at any point, they're considered severe as well. So these storms need those three conditions, but they also need great vertical wind shear. So a rapid change in wind speed and or direction with height, and I'll show why that's important. Here's looking on the left here without wind shear. You'll get an updraft in a thunderstorm, and I'm showing no wind shear over here, just no change in the wind speed with height. So the updraft comes up, starts to form condensation as that air expands and cools to its dew point. Let's say that that condensation eventually leads to precipitation. That precipitation will then start to evaporate as it falls beneath the base of the cloud into an unsaturated environment. So two things add up to what's called a downdraft. The evaporation of the raindrops cools the air, making it want to sink. Also, the raindrops physically push the air down as well. So that creates a downdraft. So without wind shear, the downdraft will happen in the same location as the updraft. So without wind shear, the downdraft chokes off the updraft within about an hour, leading to a very weak and short-lived storm known as an air mass thunderstorm. With wind shear, completely different animal. Here I'm simply showing the wind speed increasing with height. And in this case, the updraft happens, it gets tilted to the right in this picture, which means all the precipitation will start to form around the top of that updraft, and then that precipitation, which has a sizable amount of weight behind it, will fall more or less straight down from where it started. The key here is it does not fall down the updraft, so it allows the updraft to continue pumping moist air into the storm, forcing more precipitation, forcing a stronger downdraft, and it's a more efficient machine. So wind shear really is needed to create a stronger thunderstorm. Now, where can you find really good sources of wind shear? Well, typically along the Great Plains, we have these extratropical cyclones that I described in Chapter 7. A low pressure system with cyclonic rotation around it is going to drag a cold front down around the west side of the low, drag a warm front up on the east side of the low. This cold front seems to be a really good mechanism for a trigger. First of all, it's lifting that warm, moist air coming in from the Gulf of Mexico. And also, there's a lot of wind shear around these fronts. Here you can see that the winds are coming from the south on the east side of the cold front, and they're coming more from the northwest or west on the back side of the cold front. That means there's a great amount of wind shear, or a change of wind speed or direction with height, which can tilt those storms leading them to be stronger. On the lower right here is a radar image showing a line of a squall line forming around a cold front. I'd like to note here that also one of the things that happens in the Great Plains, since we have a source of continental tropical air, that is dry air, dry warm air in the southwest deserts, that can also play a factor. It gets pulled sometimes down along here. Instead of a cold front, you might have what's called a dry line, which is where you have really dry air that's warm hitting really moist air that's warm. And even if they're at the same exact temperature, that's still a front because the dry air is more dense than the moist air. So it can dig under and lift that moist air just like the cold front does. So we have two ways to really generate these squall lines. Could be along a dry line getting pulled along these extratropical cyclones on the south sector, or it could be a cold front like shown here sweeping around the bottom south side of that cyclone. The main point here for climatology is that there is a connection between the jet, which can force these large-scale low pressures and these large-scale fronts, and the strong thunderstorms. So they give them these really nice triggers, really nice wind shears, so you have these really strong, severe storms associated with the jet stream. So here we're looking at the distribution of severe storms over month in the United States, specifically around Oklahoma here. And so we're looking at the white column, severe thunderstorms. Again, the categories are large hail or very strong straight line winds, or the black columns are a subset of those. Those are severe storms that also involve the tornadic storms. In both cases, they're most frequent during spring or very early summer, say May, early June. So why is it that spring and very early summer have the most severe storms in the Oklahoma area? A, makes a lot of sense. There's more fronts around because at this time in the winter, I showed that the jet stream is at its maximum southward extent. So it's around the middle of the country. Let's say it clips around Texas during the middle of the winter. And then as we move into summer, that whole jet stream, which follows the temperature gradient, migrates to the north. And with it, the large-scale extratropical cyclones and the fronts it pushes around. So during spring and early summer, you still have that jet close enough around Oklahoma to give you these big fronts and the big wind shear and the big lifting mechanisms. Another part that's important is that now you're starting to have very long days. So you're going to start to have a warm ground, but the upper atmosphere doesn't respond to that initially. It's still cold. What this means is it actually leads to a more unstable atmosphere in the spring and early summer compared to later in the summer. You can compare this to the oceans, where we found that in the tropical ocean columns, a warm fluid on top of a colder fluid beneath was a very stable situation. The same thing holds for the atmosphere, which you can consider a fluid. If in the springtime you're starting to warm the bottom of the atmosphere because you're absorbing solar radiation at the ground for the most part, and then the residually part of the upper atmosphere is still cold, now you have a warm fluid underneath a cold fluid, and that wants to turn over or be unstable. And this is why it's more unstable during the spring, early summer than later. Now part C is a little trickery here. There is not more water vapor around in spring and early summer compared to mid and late summer. It's actually just the reverse. So my point here, and the right answer for this question would be D, A and B only. My point here was that really what creates very strong thunderstorms is the fact that you have instability plus good wind shear around. The water vapor is obviously needed, but these things are more important to make the thunderstorms really severe. Here's looking at the distribution of severe thunderstorm events in the United States in 2006. It's an arbitrary year here. It's a typical year though. The distribution of hail, the distribution of straight line winds here or tornadic winds. What you immediately see in this distribution is that most of these strong severe storms happen in the Great Plains. A couple of reasons in this. From chapter 7, we found that there's a lot of places for cyclogenesis where you can get these large-scale low-pressure systems that have fronts associated with them, good wind shear, thus good environment once summer or spring comes to get thunderstorm formation. That's the real big factor. If you step back a little bit, another factor is this is a good place, being really flat land, for cold air masses that are dry coming from the Arctic area colliding with really moist warm air masses coming from the Gulf of Mexico. They don't seem to mix very well. In fact, they create these fronts, they create thunderstorms, etc. So that's kind of the overarching reason why this happens in the Great Plains preferentially. Lightning. Here's looking at the distribution from 1989 to 1998. Lightning strikes per square kilometer per year in the US. And we do have a lightning network around the United States that can measure every stroke of lightning. So we can see clearly that Florida is the clear winner in lightning strikes, which means they have the most thunderstorms there. Why do they have the most thunderstorms? Well, you can essentially think of it as a hot plate here. As Florida tends to get warm, air wants to rise. As it rises over Florida, it must be replaced by air at low levels, so it pulls in moist air from both sides of the peninsula in what's called a double sea breeze effect. So then you have a convergence of moist air coming over the continent, forced to rise up, giving you a lot of thunderstorms. That's the primary reason why Florida is the king of lightning strikes there. But you can also see the Great Plains in general are a hotbed of lightning strikes as well. Panning back to look at the whole globe, lightning strikes per square kilometer per year, we see that there's many more strikes over land than ocean, and this is due to daytime surface heating of the land. This tends to destabilize the atmosphere in the afternoon and can also provide that initial trigger as well. The Congo in particular is a hotbed of lightning. It's kind of like the double sea breeze effect on maybe a larger scale than Florida, and they also have some mountains that influence the surface heating and give them even better chances of thunderstorms and lightning there. How lightning and atmospheric chemistry work: lightning is hot enough, 5 times as hot as the surface of the sun, to split molecular nitrogen and molecular oxygen, and those products can go on to create ozone. So wherever lightning's happening, you're getting production of ozone. In fact, some people can smell this happening when lightning strikes nearby. Fossil fuel burning certainly creates ozone as well, and it does create more ozone these days than lightning does near the surface. However, if you go up to about 3 to 8 miles up during summer, lightning is a more significant source of ozone than fossil fuel burning. So it is something you have to consider when you're looking at atmospheric chemistry. And so ozone is a greenhouse gas. So when it's in the troposphere, it acts just like any other greenhouse gas, trapping in infrared radiation near the surface. Lightning and forest fires. Approximately 12,000 forest fires are started by lightning each year in the United States, burning around 4.6 million acres per year. The primary cause of these fires are humans. One study said about 84% are caused by humans. How does the area burned by human-caused versus lightning-caused fires compare? Well, there's a much greater acreage caused by fires started by lightning, 4.6 million acres, like I mentioned, compared to human-induced fires, which is around half of that at 2.5 million acres. The reason is fires started by lightning tend to be in remote areas and take longer to detect. They get a much greater head start than the ones that are caused by humans. Colorado has seen some serious fires in recent years, like the Hayman Fire in 2003. This one, I'm looking at the West Fork Complex near Wolf Creek Pass in southern Colorado. This was 2013. It was extremely large and hot fire, one of the hottest fires on record. It was caused by lightning, and then it was fanned by 40-mile-per-hour winds for about 10 days, which really exploded the fire. This is a picture I took on the west side of Wolf Creek Pass, looking at the West Fork Fire in its infancy. It had just started the day prior. Because of the high winds, aircraft were grounded for many days, and actually because of the heat here, in part because the winds fanned it, but also because it's burning into a lot of beetle kill, the extreme heat actually evaporated a lot of the slurry, the retardant they dropped from planes, before it hit the ground. So they had to use a bunch of techniques to prevent that from happening. Here's actually later on, right before evacuations occurred in South Fork, which is on the east side of Wolf Creek Pass. We're looking at the fire on the west side of Wolf Creek Pass burning, and you can see how hot it is at this point. And here's looking from a satellite shot from the International Space Station. You can see extreme heat kind of forcing convection off of this. And here's the main part of the complex. It was called a complex because it was a system of several fires. And here's Wolf Creek Pass Road itself. And this part's on the north side of that. Here's a small section of this complex, and this one's actually burning right on the ridge where Wolf Creek Ski Area is. An interesting story, one of the lifts is right here, kind of downwind of this heat, and actually the owner of Wolf Creek Ski Area was out there with a lot of water cooling down the cables of his very expensive chairlift, trying to prevent damage, and he'd actually managed to do that. This one got put out pretty quickly as well. Science is a scientific journal, peer-reviewed articles are in there, and it's well known throughout climatology and atmospheric science. And here's a study in there, projected increase in lightning strikes in the United States due to global warming. This one study, and it's just one study, we always have to think about how many studies say the same thing. This one thing predicts a 50% increase in lightning by 2100. So we'll have to keep that in the back of our minds. I'm not saying that's true or not, I'm just saying one study suggests that. Other studies show 5% to as much as 100% increase. Most of the studies do show an increase, though, in lightning strikes. So we'll have to really think about that when we're looking at projections in the future, because obviously you're going to have lightning around, you're probably going to have rainfall around, but you're also going to have warming surfaces, so how much evaporation, what's the land surface going to look like? If you have lightning in a place that has evaporation rates that are high and a dry land surface, you could certainly expect more wildfires, and most of the studies project more wildfires in the future, at least in the mid-latitude zone. Let's switch gears here and look at tornadoes. Here's a scale of tornado strength, what's called the Fujita scale, and then the enhanced Fujita scale. These are both based on the damage caused by a tornado, and they give estimates for the associated wind speeds. So essentially what these scales are, and the difference is that the Fujita scale, the engineers who went out there and assessed the damage, did not think the relationship between the damage and the estimates of wind speed for the original Fujita scale was that accurate, so they made an enhanced Fujita scale that they thought was more accurate. But at the end of the day, we don't go into the middle of a tornado and actually get the wind speed directly. We actually look at the damage it causes. Based on that damage, we can figure out how fast the winds must have been going to cause that damage, and then we classify those storms as a result. Now it turns out the strongest thunderstorms are actually what are called supercells. In addition to having that wind shear, which isn't particularly well drawn here actually, but in addition to having wind shear, they also feature what's called a rotating updraft, described as a mesocyclone. How this happens, you could get wind shear, what's called a vortex tube on the surface here in the upper left. If that's rolling around the plains and then it gets sucked into an updraft and gets tilted upwards, it can actually realign itself, so now it's a rotating updraft. This is important for a variety of things with thunderstorms. However, for our scope, I'm going to try to keep it as simple as possible. A mesocyclone is not a tornado. It is a rotating updraft. It's much larger in scale than tornado at 3 to 10 kilometers. However, tornadoes are often associated with mesocyclones. In other words, tornadoes are often associated with supercells. In fact, the strongest tornadoes are always associated with supercells. One feature of having a rotating updraft is interesting. In this case, most of these things form along extratropical cyclones, and in the environment between an upper level trough and an upper level ridge, you'll find that that's primarily southwest winds. So these things tend to propagate across the Great Plains from southwest to the northeast, getting pushed with the main flow of the upper level winds. What's interesting with these, that rotating updraft, here shown in yellow, actually prevents winds that are hitting from the southwest into the storm. So what happens is you get some precipitation associated with the updraft. These winds that slam into the side of the supercell actually are forced to cool from evaporation of those raindrops, and you get what's called a rear flank downdraft on the back side of the storm. Since the primary winds are from the southwest, a lot of the precipitation gets thrown forward of the storm in what's called the forward flank downdraft. And this is a zone, again, where there's a lot of precipitation evaporation causing a downdraft. So the supercells do have two distinct downdrafts. That becomes important because what happens, the downdrafts both spread out horizontally when they hit the ground in all directions. This rear flank downdraft tends to get wrapped and pulled around, shown as a gust front here, which is just kind of a mini cold front associated with that cold air that's moving along the surface of the ground. That meets up with the other gust front coming from the forward flank downdraft. And what happens next is very interesting. These two gust fronts, or essentially two cold masses of air, tend to choke off the bottom of the updraft. And what happens next is a process called vortex stretching that I'll show you how it works. What causes a tornado? There's actually a lot of complex ways that I don't need to get into in a climatology class, but the most important thing is vortex stretching. Here we can show the vortex stretching. Here's one vortex, and we looked at this when we explained conservation of angular momentum for the Coriolis force. If this cylinder is rotating at some speed, some set velocity, and it has a set radius, the product of those two things, as long as the mass is conserved, the product of velocity times radius must be conserved as it gets stretched vertically. When it gets stretched vertically, of course, the radius goes down, so the velocity has to go up. For a supercell tornado, those two downdrafts really wrap around the updraft's bottom, choking off the bottom of the updraft. The upper section of the updraft keeps rising, however, and this really does physically stretch out that vortex or stretch out the mesocyclone in a process just like this in the upper right. This forces that mesocyclone to become thinner and to spin faster, and eventually this can lead to tornadoes. Now, if you dig deeper into literature, you'll see that there's many complex processes before a real tornado is made. However, this vortex stretching is important, and it happens a lot with the mesocyclones, and that is correlated with how many tornadoes you might get out of a supercell. Other weaker tornadoes can form in a similar process, just having any kind of wind shear driven circulation, say wind shear at the surface, just like the mesocyclone was created along Florida. This happens a lot, where you just have wind shear at the surface, you have plenty of thunderstorms, they pull those vortex tubes up and stretch them out. You can actually get weak tornadoes that way. But again, the world's strongest tornadoes are associated with these larger scale mesocyclones, which are embedded in supercell thunderstorms. A really interesting factor about this is because at the same time, these two gust fronts choke off the updraft and cause a tornado, so it's really killing the updraft at the same time it's causing that tornado, it actually leads to these converge to the southeast of where that updraft died, where that tornado ended, and so now there's a new lifting mechanism to form a new updraft. So the same supercell, which are very large storms, can actually create more updrafts, and each time you get a new one that gets choked off, you might get another tornado. So you get what's called tornado families that tend to propagate, again, from southwest to northeast, following the line of the supercells themselves across the Great Plains. Here's an example of that. Super outbreak of April in 1974. Supercells formed ahead of a cold front, again associated with an extratropical cyclone and ultimately the jet stream. The largest tornado outbreak recorded in the U.S. until 2011, which was an even bigger one. 335 people were killed, 5,500 injured, almost 150 tornadoes formed. 76% of those occurred in tornado families. So this is why I bring out this rather subtle mechanism, because it's actually important in how many tornadoes are formed. You can see all these lines are tornado families, tornadoes formed by different updrafts within the same supercell. Looking again at the distribution of severe thunderstorms in the United States, 2006, why the Great Plains again? Again, this is a good flat area for cold and warm air masses to mix together. Cyclones tend to form east of the Rockies and near the Gulf of Mexico, helping to mix these air masses together. These collisions are known as fronts, and the fronts have wind shear, which can give you stronger thunderstorms, and can also lead to supercell thunderstorms, which have a rotating updraft. Since supercell thunderstorms are often associated with tornadoes, this explains why 75% of the world's tornadoes actually occur on the Great Plains. So this is an effective mechanism for severe thunderstorms and the resulting tornadoes from them. Here's a tornado frequency per unit area across the U.S. We have a region called Tornado Alley here, stretching from Texas up through Nebraska, and also there's another secondary area called Dixie Alley that also has a high frequency in the southeast states. And what's shown here is actually the frequency of all tornadoes here. In Florida, we see that actually is the highest frequency of tornadoes in the United States. However, what's shown in parentheses are stronger tornadoes, going from EF2s to the strongest, the EF5 tornadoes, the really strong ones, would say 200 mile an hour of winds. Very few of those in Florida, but a lot of weak tornadoes. The place that has the most strong tornadoes would be Oklahoma, so they have a lot of supercells, which are giving the world's strongest tornadoes. So Florida definitely has a lot of thunderstorms, a lot of chances to take any kind of wind shear at the surface and pull it up and stretch it out, forming a weak tornado. But to get the supercells, you need to be closer to where these extratropical cyclones are giving the more large-scale fronts, the more extreme cases of wind shear, and that's when you get your strong tornadoes forming from that type of environment. What time of year are tornadoes most common? Tornadoes occur year-round, but are most common from April through June. Why are tornadoes most common at this time of year? Simply said, this is a time where the jet stream's still close enough, it's still across most of the United States, It's starting to head to its northward position along the border with Canada, but it's still within the United States, still around to give strong fronts that can drive strong storms and strong tornadoes. Of course, you also need to have some surface warming to drive instability, so there's kind of a balance there. You want the jet stream around for the wind shear, and you also want some surface warming. The best of both worlds happens around May, and that's when we have the most strong tornadoes. Just as a final aside, here's an EF5 tornado track. You can clearly see from this aerial footage, it really does quite a bit of damage. If you came close to the ground here, you would see that all these houses are stripped right down to their foundation. Almost nothing is left in the track of an EF5. As far as climate change and tornadoes, there's no real hard conclusive evidence there. It's hard to model these small-scale features over long time scales. Some models say more instability with less shear in the future, so more thunderstorms but more weak thunderstorms specifically. Other studies suggest more severe thunderstorms in a warming world. It doesn't necessarily mean more tornadoes though, even if the parent storms are more frequent or stronger. You can't explicitly say that. It's just simply a real hard thing to model in the future and to predict. So, summary from part 1 of chapter 8, thunderstorms. The ITCZ has frequent rainfall from thunderstorms that came out in the lightning density map across the globe. Strong mid-latitude thunderstorms require wind shear, which is in abundance around large-scale fronts from jet-driven cyclones. The distribution of severe thunderstorms across the U.S. therefore tends to follow the position of the jet heading north from early spring to summer. For instance, Texas gets their most severe thunderstorms in April. As you go north, the most severe thunderstorms in, say, Chicago is more in July, when again the jet is closer to them at that part because the jet migrates north over the course of the summer. Most studies predict increases in thunderstorms of one variety of another with future warming. Lightning is an electrical discharge from thunderstorms. We did not get into the mechanisms of how that forms. Lightning can lead to ozone in the upper troposphere, so it's important for atmospheric chemistry. Lightning causes the largest wildfires in North America, so that's certainly important, and we'll tie this into aerosols and the concentration of particles in the atmosphere as well as the deposition of black soot on the surface of Greenland and how it impacts meltdown there. Lightning strikes are projected to increase with future warming. For tornadoes, 75% are found in the Great Plains, so this is really a hotbed globally for tornadoes. It's due to that flat surface having cold and warm air collide, causing fronts, wind shear, and associated severe thunderstorms. Most of the tornadoes occur in April and May due to the combination of unstable air with a warming surface now and residually cold upper atmosphere, plus fronts and wind shear around because you have those extratropical cyclones driven by the jet around. Florida has lots of weak tornadoes due to the fact that they have a lot of thunderstorms enabling vortex stretching all the time, but they are not close enough to the large-scale fronts needed for supercell thunderstorms that drive stronger tornadoes. The science is certainly not solid on the future number of tornadoes.